introduce Professor Francesco Buscemi. He got his PhD in theoretical physics from the University of Pavia, Italy in 2006, under the supervision of Professor Dariano. After postdocing in Tokyo University with Professor Imai in Erato SOR sourced project in quantum computation and information, and also Cambridge Statistical Laboratory. Since 2009, he is with the Graduate School of Informatics of Nagoya University, Japan, where he became full professor in 2019, last year. He serves in the editorial boards of several specialized journals, including the recently launched American Physical Society journal, PRX Quantum. And in the year 2018, he was awarded the Birkhoff von Neumann Prize by the International Quantum Structures Association for his work on quantum foundations and mathematical statistics. And Professor Francesco Buscemi is working for the Department of Mathematical Informatics in Nagoya University. And he is going to talk on quantum entanglement from basic question to technological resource. If you have a question, please put it in the chatting box, and also you can ask later. And the talk will be about an hour, and it could be longer than that. And we are going to have a 1 hour and 30-minute session. So after the main talk, you can ask any questions to Francesco. So let's welcome Francesco here. Go ahead, Francesco.
Thank you very much. Can you hear me?
Yes.
Okay. Thank you very much for the very kind invitation. It's really a pleasure to give this colloquium in this series. And of course, it would have been nicer if we could have organized something face-to-face, but this is what we learned recently. And actually, probably, you know what, that for the planet as a whole, avoiding unnecessary flights, it might not be such a bad idea after all. So anyway, I'm happy today to share with you some research that I've been doing in the past, I would say, 8-10 years, a kind of common thread that relates some of the things I've been doing lately, which is at the boundary between the foundations of quantum theory and quantum information theory, but also something on mathematical statistics. So let me share my slides. Okay. Right, I hope you can all see those. Is the share gone fine?
Yeah, it's
successful.
Yeah, it looks okay.
So the main role, the main character we are going to talk about today is quantum entanglement. That started as a problem. Actually, it was something that was introduced as a trouble for quantum theory, and quite ironically, it turned from being a trouble of quantum theory to being quantum theory's most valuable resource, because now quantum entanglement is served as the launch pad of all these new emerging quantum technologies. There would be no quantum computer, there would be no quantum cryptography, there would be no quantum technology, whatever you may think of it, without quantum entanglement. So it's a beautiful parable in a sense that something that starts as a problem, as a puzzle, as a paradox, turns out to be actually the most valuable asset of a theory. Okay, so the first part is about entanglement, how it came to be, why people started thinking about this feature. So here is a very short timeline of quantum entanglement in science. So quantum entanglement was essentially introduced. I mean, people knew that there were such things as entangled states in quantum theory, but the first time that someone realized that there was something really special about entanglement was in 1935, in a very famous paper by Einstein, Podolsky, and Rosen, the so-called EPR paper, and two papers that were published just after that, actually in response to the EPR paper by Schrödinger in 35 and 36. So at the time, people realized that entanglement was posing a threat to the integrity, to the completeness, actually, to be more precise, of quantum theory. But the discussions at the time were kind of metaphysical, in the sense that there was no clear experimental scenario being described there. In a sense, entanglement was not considered, I mean, the problem was not formulated in a way that could be falsified in an experiment. And we know that falsification is the main character of science. Everything that is not falsifiable is not really physical. It's something like metaphysical. So that's why here I would say that at the beginning, the problem of quantum entanglement was more on a metaphysical level. The first analysis that brought entanglement down, let's say, to a physical level, something that could be, in principle, be falsified in an experiment, was the paper by John Bell in 1964, where a mathematical formalization of, the EPR paper, the EPR paradox, was provided. And then from them again, so now you see that there are already like 30 years have passed without any particular new insight in entanglement between the EPR paper and Bell. And then again, 20 years pass, almost 20 years pass before Bell's proposal is actually done in a lab by Elena Speck in 1981 in a series of very famous experiments. But again, at the time, entanglement was considered a kind of a weird feature, and no one really knew what to do with that. So we have to wait the early 90s with Eckert cryptographic protocols, but even more important at the time probably was the superdense coding protocol by Bennett et al. 1992 and 1993, the quantum teleportation protocol, that together with the emerging field of quantum computation essentially made it clear that entanglement was something absolutely necessary for any emerging quantum technology. So let's start by reviewing briefly the EPR argument. So why Einstein and co-workers thought that entanglement would be bad. So as you know, even if you are not actually working in quantum information theory, but it is a very basic fact that quantum states in quantum theory are described by unit vectors in complex vector spaces, so like d-dimensional rows of complex numbers. And an important postulate of quantum theory tells us that composite systems are described by unit vectors in the tensor product of the Hilbert spaces of the components. And so it means that you have not only states that are product states, but also linear combinations of these things, linear superpositions of these things. So it means that you have entangled states like this one. Okay, so what is it? This is a phi plus. And you see that you can write this thing as a superposition of the spin. So by the arrow up z, I mean the spin in the direction up of the spin observable in the direction z. So I'm in a two-dimensional Hilbert space here. So you have the superposition between both particles being pointing up and both particles pointing down in the z direction. But as a matter of fact, this state is exactly the same and can be written also in this form, where now the correlations happen to be in the x direction. Okay? And this was a problem. Why? So we see that you have correlations both in the z direction and in the x direction. So why it was meant to be a problem, was understood as a problem by Einstein and coworkers? Because a measure on a choice that you do on system A is able to collapse system B on different bases. So suppose that you decide to measure the spin in the z direction on A. This means that you are in this representation of your state. And so it means that the B system collapses either on up Z or down Z. So it means that if you decide to measure Z on A, Z becomes a real quantity for system B. Analogously, instead, if you decide to measure A in the X direction, then X would become a real property for system B. So I use a lot of scare quotes here. There is an abundance of scare quotes because these words like real, collapse, true, these kind of words have been used too often by too many philosophers and physicists and people. So, you know, I'm not sure that I'm using them properly, but we can understand what we mean by that. So what it means that a choice done by system A can decide what is real on system B, according to the definition that EPR gives of real. And this effect happens instantaneously, because now you can imagine that particle A and particle B are very far apart, but however far they are, a choice of a measurement on A decides what's real on B. Point is that X and Z cannot be real at the same time because they do not commute. And so here you have a contradiction. It means that really a measurement of A has this kind of spooky action that materializes, realizes two things that cannot be real at the same time on system B, and does it instantaneously. So, you know, violating special relativity. This was a problem. So for EPR, the problem was quantum theory that was not complete. Now, of course, we know that the story should be told in a different way, but it was presented as a problem. But as you see, as it is now here described, still we wouldn't know what kind of experiment we should perform, because the notion of reality is given in a kind of abstract definition. So what kind of experiment you should carry on in order to prove or disprove this EPR conclusion. So here comes Bell's formalization, which happens to be published almost 30 years after EPR proposal. And the crucial point in Bell, one of the crucial ideas in Bell's paper, is that it gives a definition, a clear definition of what local realism should mean, like how local realism, that was a kind of abstract idea in the EPR paper, how this should be written as a mathematical formula. And he suggests that classical correlations, so like correlations that follow this local realism principle of EPR paper, should be those that can be decomposed in this way. So you see that there is some common source that sends out some signals to A and B, the same signal lambda, and then these input-output correlations are factorized in this way. So for example, on Alice's part, you see that the statistical rule that describes the functioning of Alice's apparatus only takes into account this hidden variable lambda and then the local variable x to output A. And the same does for B. So in this way, you have a clear and neat characterization of what it means to be local and realistic according to EPR. Whereas, if you consider that lambda can output any bipartite quantum state, you know that quantum theory tells you that this correlation should be computed in this way. So this lambda AB is a bipartite state. The part A goes to Alice, the part B goes to Bob, and then they perform measurements that depend on their input, X and Y, and output, statistically, outcome A for Alice and outcome B for Bob. Okay, so now the second important step in the derivation of Bell inside is to realize that the set of classical correlations form a convex subset among all possible quantum correlations. So here I drew it as CC, classical correlation, as a closed convex subset within the set of correlations that you can obtain according to quantum theory. And so what it means that if you have something that is not a classical correlation, like this point outside the subset CC, then there should exist a hyperplane, this blue line, that is able to witness the separation between these. This is the crucial insight of a Bell inequality. So I would like to be a bit more concrete now and give you an actual example of probably the simplest Bell inequality that one can derive. This is given by the famous example of the CHSH game, which is an acronym for the authors of the paper that was published, I think, just 5 years, 1969, after the paper of Bell, and it's Clauser, Horn, Shimoni, and Holt. So they invent this inequality that is now usually formulated as a kind of game because it makes a more compelling story to tell. So you imagine that there is a referee and there are two players, Alice and Bob, that are separated. They're put in different rooms, and we are making sure that they won't be able to cheat. So cheat here means that they won't be able to secretly communicate with each other. And now the game is as follows. The referee will hand them randomly the questions X and Y. So the question X is given only to Alice, the question Y is given only to Bob. And without communicating, Alice and Bob have to give back to the referee the answers A and B. A is Alice's answer, B is Bob's answer. And this is the winning table. So you see, for example, if the referee asks both Alice and Bob question 0, then Bob and Alice will win if and only if either they both reply 0 or they both reply with a 1. In all other cases, they just lose. So this is why this game is sometimes known also as the XOR, exclusive OR game, because you want that the end of the questions, right, you are taking the product of the question is equal to the exclusive OR of the answers. So now let's think about what can happen here. So first of all, how do you compute the winning probability of this thing? Well, if you imagine that these 4 possible patterns for the questions are randomly chosen, then you have this 1/4 at the beginning, and then you have the probability, right, that A and B are output given that the questions were X and Y, times this delta function, that is the delta function that corresponds to the winning condition. So if you see here, and you imagine that this summation is actually a scalar product between 2 real vectors, a vector P, which is the vector that represents this correlation, PAB given XY, and a vector F, which is a vector that represents, a vector that encodes the winning condition of the XOR game, you see that this becomes, the winning probability is a linear function of P. And now we are going to put bounds on this. So we are exactly doing what we've seen before, right? We're putting bounds on a linear condition here. And the bound is that if Alice and Bob can only sample using an element of this classical correlation subset. So if Alice and Bob can only build up classical correlations between themselves, it is easy to prove that the maximum winning probability is 0.75. However, if Alice and Bob can exploit quantum theory and create quantum correlations, it is possible to prove that they can win this game 85% of the times. So they can violate this bound. So the classical bound is the Bell inequality that corresponds to the CHSH game, and it is violated with quantum correlations. This is also the famous Tsirason bound, the famous 2 square root of 2 that is coming up in so many areas in the study of quantum correlations. And one more thing I would like to tell you, because it will be useful later on. What if Alice and Bob can communicate? They can win always, right? Because Alice can just tell Bob which questions she has gotten, and then Bob knows what kind of answer he has to give in order to win. So a Bell inequality, a Bell test is usually made trivial by classical communication, even just one-way classical communication. Let's keep this in mind because it will be useful later on. And then, as I said, from paradox, in the early 90s, we realized, the community, the scientific community realized that quantum entanglement instead can actually be useful. And the most important things are, one, Eckert cryptographic protocol, but also Bennett-Brassard-Mermin cryptographic protocol that also uses entanglement, but also super dense coding and quantum teleportation. So now entanglement really is crucial to the design and development of quantum technologies. We couldn't do anything without quantum entanglement. So now the point is, how can we verify if entanglement is there in a source? Suppose that you buy a source from a producer, and now you want to verify whether entanglement is there. Why you want to verify? Because entanglement is crucial for quantum technologies. So how can we test, or how can we benchmark entanglement? So this question brings us to considering statistical tests for quantumness. So I want to stress here that I will be speaking about statistical tests because there are other tests, so-called, like, for example, computational tests of quantumness, where people want to check whether a computing machine is actually able to do quantum computation. These are a completely different family of tests. So here we will focus on statistical tests instead, that are basically, by collecting the data of some experiment, you want to know how likely it is that your source produces entangled states. So how to observe entanglement? So the first proposal is by using quantum tomography. Quantum tomography is nowadays a very well-known procedure to reconstruct a quantum state, even a bipartite quantum state, by classically post-processing the data acquired by local measurements. So you can take system A and make it undergo some measurement there. System B, it undergoes another measurement, an independent measurement. And then you combine the data in a classical computer, and you can use this data to reconstruct the source and the correlations within the source from local measurements. And then once you have a reconstruction, then you can compute how likely it is that the source is emitting entangled signals. But now there is a problem in quantum tomography. And okay, the technical word here, if you want to look more into this, is entanglement witnesses. So this method to do tomography basically, and then use the tomographic reconstruction to compute entanglement, is something that is known as entanglement witnessing. But there is a problem with this approach. And the problem is that in order to do tomography, you need fully trusted, perfectly known measuring devices. In the sense that if here the actual devices deviate from what you think they are, then your reconstruction is completely astray. your reconstruction will lead you astray, and your reconstruction will give you false idea of what's actually going on in the source. And you can imagine.
Can I ask a question?
Yes, sure.
Excuse me, Francisco. I mean, as far as I know, entanglement is non-local, non-local correlation. But you are telling us about local test, basically local measurement. How can you, get information about non-local property only by using local measurement? I mean,
it's surprising, isn't it? But that's the core of quantum theory. Quantum theory is a theory where you can just do local tomography and still you're able to reconstruct a non-local signal, because everything is linear. The point is that here the things are linear. And so if you have a complete measurement, a complete quorum of measurement on each system, by linearity, you're able to reconstruct also the correlations. Yes, I agree with you that it's surprising, but that's how it works.
Well, I mean, it happens maybe only two-level systems, but in multi-level systems, there are many, infinitely increasing number of correlations.
No. You can do with continuous variables as well. You can do when you have infinite degrees of freedom. Okay. Trust me. I mean, this is a very well-known field. It's called quantum tomography, and I mean, it is done routinely in the laboratories since the 90s. It's surprising. I agree with you. Very surprising, but that's how it works.
Okay.
Okay. But there is a problem with quantum tomography, and the problem is that you have to know exactly what are the measurements that you're doing, because the measurement that you're doing are what decide how the reconstruction of the wave function is made on your classical computer. So if you're collecting data in a wrong way, so to say, then the reconstruction will be wrong. And it could be that you think you have an entangled source when you have no entanglement whatsoever there. So this is a problem of quantum tomography. And this is one of the main reasons why people then introduced what is known nowadays as device-independent test of entanglement. This is something probably that Professor Scarani will tell you better next week. He's an expert. He's one of the people that used device-independent protocols from the beginning. So what happens if we don't trust the measuring devices? Actually, we should never trust our measuring devices. There could be some source of noise that we cannot control in them, right? So in this case, Bell tests come to the rescue. Why? Because imagine that you have a Bell test set up in your laboratory, and imagine that you actually register a statistically relevant violation of a Bell inequality, any Bell inequality. Because, by the way, there are infinitely many Bell inequalities, not just the CHSH game I showed you before. There are infinitely many of them. So suppose that you register a statistically relevant violation of any Bell inequality. This means that you have registered a correlation that happens to be outside the set of classical correlations. And so what you can conclude, there is not much you can conclude. You can conclude that it's not classical. And then if you believe that the thing instead is quantum, then it should be quantum entangled source. So you can rule out, you can falsify in a device independent way, because then it doesn't matter how you collected the data, right? You see? It just have that you are given some body of data, some data coming out from an experiment. And if you can rule out any loophole, then you are left. The only thing that you can conclude is that the correlation that was produced there was something outside the set of classical correlation. And therefore, you are led to conclude that there was something non-classical going on there. that is quantum entanglement. But there is a trade-off here. And, you know, we just gave up, we just could solve the problem of the trust in the measuring device, but here there are some problems that come up, you know, in real life. Real life is always a matter of balancing between trade-offs. And indeed, you have some drawbacks also when performing Bell tests. First of all, because you have to rule out any form of communication between A and B. Why? You should remember from the slides before about the CHSH game that if Alice and Bob can communicate, they can cheat, and they can win with probability 1. Actually, they can even win more often than quantum theory. So first of all, we have to put Alice and Bob in a situation where they cannot communicate. And how this is done in experiments usually is that these two particles are brought very far away. And then that by careful timing questions and answers, we can rule out communication, because if communication happened, this should have happened at a speed faster than the speed of light. And so by spatial relativity, one can rule out communication in experiments. So you can solve this problem with a space-like configuration, which, by the way, makes the experiment very hard. Another problem with Bell tests is that losses in the detectors can be used to cheat. So there are situations in which your detector will just not register an event. It will just not click. Even though a photon or even though a particle will hit your detector, the detector will not tell you anything. This is a loss. And inside losses, a cheater can hide. Okay, so we need also very efficient measurement devices. This was also another technological hurdle to overcome in order to do Bell tests practically in the lab. And then another problem with Bell tests is that they set the bar very high, in the sense that there exist entangled states that, even though they are genuinely entangled, they will never be able to pass any Bell inequality. There are entangled states that will only give rise to classical correlations. There is also a way around this problem, but it is a very convoluted way, and it requires a kind of concatenated Bell tests. This is a solution that appeared quite recently, 2018, but it requires a concatenated Bell test. So you need entangled states to verify entanglement. Like, you know, when people say it takes money to make money, here it takes entanglement to certify entanglement. So we have these three big problems. You need space-like configuration, very efficient detectors, and you need auxiliary systems, which are entangled as well. So it is really complicated to verify entanglement in a device-independent scenario. So now comes a little bit also my original contribution to the subject. So one might ask, so can we trade a little bit of trust for more practicality? So you see that we have two extremal cases. We have, on one side, we have quantum tomography that is able to give you the entire wave function, actually, not just the correlation. It gives you the complete information about your quantum states and quantum correlations, but it requires full knowledge of the measuring devices, which is something which is kind of hard to assess. On the other hand, you have Bell tests that are going to certify entanglement in a completely device-independent way, but they are very hard to pass. So it means that many times you will just fail a Bell test, even though your source was a good, genuinely entangled source. So can we try to find something of a sweet spot between these two extrema? So my proposal here was to move from here, which is a conventional Bell test. You see that there are questions X and Y asked and A and B output by Alice and Bob, to this. So find the difference. The difference is that the input here, the questions, are encoded on quantum states. So you use this scenario, and again, you can compute the correlations between X and Y and A and B. Just now, the questions are provided to Alice and Bob as quantum states. So these tests are what I called semi-quantum tests, and have been actually used quite often since then, because they kind of find a satisfactory balance between the flexibility of quantum tomography and the strong certification of a Bell test. Why? Because with respect to quantum tomography, now we have to trust the preparation of the question states. So we have to trust that actually tau x is prepared and omega y is prepared when we want it, but we don't need to trust the measuring devices. And you know, there is a big difference between trusting measuring device and trusting the preparation, because preparation, you can do it again and again until you're happy with the result. You can post-select on a preparation, whereas the measurement is there. You cannot cheat, because if you just throw away some bad results from the measurement, then those should be accounted as losses. And we know that in losses, there could be cheating. So here, in a sense, you just have to trust preparation, which is easier to do. Like if you ask an experimentalist, experimentalists are much happier if they have to prepare a given state rather than if they have to perform a given measurement. That's much harder to assess. But also with respect to Bell tests, you gain something, because now with semi-quantum tests, you can verify any entangled states. You remember that we were saying that with Bell tests, the bar was set very high, in the sense that there exist entangled states that will never, ever be able to pass a Bell tests. Whereas here, even if you have a very weakly entangled source, still you are able to certify it with a semi-quantum test. So they're called faithful. The key word here is faithfulness. Semi-quantum tests are faithful, Bell tests are not. And another feature of semi-quantum tests is that they are robust against classical communication and losses. Why? Because just they don't care about the measurement. But I would like to come back a little bit more on the feature of being robust against classical communication. So what does it mean? It means that if you have two players, Alice and Bob, by the way, you notice that Bob looks very much like myself. So if you have two players, Alice and Bob, and you give them the questions encoded on quantum states, and then you allow to exchange any sort of information over a classical channel. If this was a Bell test, they would be able to cheat. But since this is a semi-quantum test, they cannot. It is possible to prove that any amount of classical communication between the two parties, between Alice and Bob, will not help them to win the semi-quantum tests, as long as the source is not entangled. So if they're able to violate semi-quantum inequality, it means that they have entanglement to start with. Classical communication will not help.
What is written inside the box?
Nothing. It's just a lorem ipsum, you know, like this kind of something that generates random text that looks like Latin, but it's not.
Okay.
Excuse me, Francesco, yeah, one more question.
Yes.
I mean, what's a good reason that you call this scheme semi-quantum? Why is it semi-quantum? I don't know. Why is semi-quantum?
Because the questions, if you compare with the Bell tests, everything, the questions and the answers are all classical things. The questions are asked directly to Alice and Bob, and they reply with a classical answer. Whereas here, the questions are provided encoded on quantum states, whereas the answers are still classical. So you encode on quantum states only the questions to Alice and Bob, but then they just output the classical classical answer, classical letter. So in this sense, they're quantum only in the questions, but they're classical in the answers.
You lose something, right? I mean, they're not completely quantum. I mean, maybe I'm wrong, but to my understanding, you know, if you measure some unknown quantum system, then through this measurement, your system in consideration and the measurement apparatus, they will be entangled, so to speak. So that using this correlation, you can get information about measurement, I mean, state of quantum state. But in this case, as you pointed out, your measurement is not clean. I mean, so that you get some dirtiness, so to speak. So you get, that means your information through this measurement is not perfect information about your quantum system in question. So your knowledge about system is limited. So you need to pay more than, in this regard, semi-quantum. Am I right? You need to pay more, I mean, so to speak.
You have more games that you can play.
That's right, there's more games. So I'm wondering how much payment you need extra pay, you need extra make. Did you ask this question as well? I mean, I understand what you're talking about basically, but I don't think the question about more payment was not considered in this context.
What do you mean? More, like, does it cost more, you mean, to encode question on a quantum state than it is just to give the question classically? This is the cost?
Measuring apparatus cannot extract exact information about the quantum state in consideration because your measurement has a sort of dirtiness, as you pointed out.
No, I don't see the dirtiness here. I'm sorry.
Okay, since this is not a technical seminar, it's rather a colloquium. So if the question and answer goes too long, we can postpone for the individual.
Oh, right. Okay.
Question.
Maybe we can postpone, but
okay.
I'm happy to keep discussing about it. So for the time being, let's go on. And yes, so a very nice feature of semiquantum tests is that they are robust against classical communication. So now you would say, so when is this feature most useful? And of course, it is useful when we cannot rule out communication. So whenever strict no signaling cannot be enforced. So I told you before, if you remember, that in Bell tests, in order to enforce no signaling, so in order to be sure that Alice and Bob are not cheating by exchanging some classical information between each other, we are putting them far apart, but we are putting them in a space-like configuration, so that if communication happened, such communication must have happened at a speed faster than the speed of light. So in this way, we can enforce no signal. So in all other situations, unfortunately, signaling cannot be, no signaling cannot be guaranteed, right? So in particular, when communication becomes communication in time, becomes a memory. So imagine now that Bob is not actually another party, but it's actually Alice in the future. So you now see that time is going from left to right. So what is communication now? Communication in this case happens forward in time, of course, and it is just classical memory, the memory of the experimentalist. And so we cannot force the experimentalist to forget the question that we asked before. We cannot possibly rule out the eventuality of a memory being used by the experimentalist, classical memory at least. So it means that if you want to test quantumness in time, Bell tests become trivial because classical memory is there. And this is also something that is at the root of the problem with Leggett-Garg inequality, which are essentially were formulated to test quantumness in time, exactly in analogy with Bell inequalities that instead were formulated originally to test entanglement, quantumness in space. And it is known that Leggett-Garg inequality have several loopholes. Some of them cannot be closed easily. And one of them is so-called clumsiness loophole, that it is presented as this funny name, but it is actually the fact that the quantum system can carry classical memory of a previous event. So you cannot rule out memory if you are testing quantumness in time. So now the idea seems to be quite natural. So why not using semi-quantum tests in time in order to test quantumness in time? And this is actually, I mean, this can be done because you can just take a semi-quantum test and transform it. You pull it from a space-like configuration into a time-like configuration, and you have a semi-quantum tests for quantum memories. So you imagine that you give a quantum question to Alice now. You wait some time, you give another quantum question, omega y, to Alice, and then she has to give you some classical outcome. By computing the correlations that you obtain after repeating this experiment many times, you can actually verify whether Alice was able to use some quantum memory or not. So if Alice had a quantum memory available to her, she will be able to win a test, a semi-quantum test, more often than she would be able to do without a quantum memory. So it means that, in a sense, if you have semi-quantum tests to do, then you can really try to certify the flow of quantum information between any two events in space-time. They can be space-like separated, in which case you have quantum entanglement. They can be time-like separated, in which case they are tests of quantum memories, of quantum channels. So about certification, then you can say that semi-quantum tests can certify any form of quantum correlation between any two events in space-time, as long as the output can reach the referee. So if one of the two is within, for example, the boundary of an event, the event boundary of a black hole, then the answer cannot reach the experiment. But in all other cases, in principle, you can test whether there is a flow of quantum information between two events in space-time. So this was about the certification part. So let's say that semi-quantum tests have this kind of nice practical application as tools to verify or to certify quantum entanglement in a way that somehow is not as tough as a Bell test, but is not as, let's say, forgiving as quantum tomography, but somehow they find themselves their use in particular scenarios, and indeed they have been used since then by quite a few experimental groups. But the thing for which they were introduced in the first place is because they have a nice connection with the theory of statistical comparison in mathematical statistics. And let me tell you what is this all about. So first of all, what is the theory of statistical comparison? So this is a branch of mathematical statistics that can be considered a generalization of the theory of majorization, which started in the 20s, in the 30s, in classical mathematical statistics. There is nothing quantum to start with. And the idea is that you want to compare statistical experiments, the informativeness, how much information is encoded in a statistical experiment. So let's be a bit more concrete here. So what is a statistical experiment? So suppose that you have an unknown parameter that you want to estimate, let's say some theta, but you cannot directly access theta. You can only prepare an experiment whose samples are distributed in a way that depends on theta. So the value of theta influences the distribution of the sample. For example, you want to know what kind of bacteria you have there. So what you do is that you prepare many in vitro cultures of this bacteria, you let evolve this bacteria, and the distribution of this growth will tell you something about the bacteria that you actually have, that you actually are observing. So the statistical dependence of a statistical experiment is given by a conditional probability distribution, the probability of X given theta. So if you give me these numbers, you gave me what mathematical statisticians call a statistical experiment. So let's think that statistical experiments are nothing but conditional probability distributions. And now you can think of comparing two. Suppose that you are trying to get information about the same natural phenomenon, the same parameter theta, but you have two different experimental procedures to get information about theta. One described by P and another described by Q of Y given theta. And now you might ask, which one should I perform? If I can perform both, given that other conditions are the same, which one should I perform? So this leads to the notion of comparison of statistical experiment that can be like sloppily summarized by the question, which experiment is more informative about theta? You want to get information about theta. Now there is, of course, like the technical thing, like you have to tell me what you mean by more informative, like that, you know, a mathematician cannot proceed. You have to give me a clear mathematical definition. And I don't want to go into the details, but let's say that more informative means that one experiment is going to yield better values in statistical tests that at the time were called statistical games. The theory of statistical comparison is something that also originated the theory of games in the 40s. And so that's why at the time people were speaking about statistical games. Now we would call them statistical tests, or even better, statistical decision problems. But anyway, there are some set of things that you can do with your statistical experiments that can measure the information content of it. And a central result in this theory is the so-called Blackwell-Sherman-Stein Theorem, that is a theorem that evolved in a series of papers by these three people separately. So they never wrote a paper together, but Blackwell and then Sherman and then Stein, they wrote a series of papers between 48 and 53 in which the final result looked as follows. So a statistical experiment P is more informative than Q if and only if there exists a stochastic transformation. So another conditional probability distribution of Y given X this time, such that Q is, you see what it is. It is kind of the post-processing of P according to L. So you take the samples from P and you garble them up according to the stochastic transformation lambda. This is the action of a noisy channel. In information theory, this is just a discrete noisy channel acting on X. There is also the idea of simulability here. If you give me P, just by appending this extra lambda after P, I can simulate the statistics of experiment Q. Even though I do not perform Q explicitly, I can just simulate Q by means of lambda. So in this case, P is more informative. So it's also related to the notion of statistical sufficiency in mathematical statistics. So in that way, you would say that P is sufficient for Q, for experiment Q. It is enough for you to do P to simulate Q. So can we have a kind of Blackwell theorem for entanglement? Now, this is the question, right? So here we were doing, you know, that you have that the objects that you are comparing are statistical experiment, but the way you're comparing them is by doing statistical tests on them. And then if one gives you better value than another one in all statistical tests that you can come up with, then you know that there exists a simulation procedure that transforms P into Q. So something similar can be done for entanglement. Like, can we say that if you have two sources that emits possibly entangled signals, and then one source, for example, is going to give a stronger violation of Bell inequalities, for example, than the other source, can we conclude anything about the existence of a kind of simulation procedure. So can one source, the source that gives you better violation, higher violation of Bell inequalities, can this source simulate the other one in some sense? Well, with Bell inequalities, unfortunately not. There is no real notion of simulability that appears, but if instead of Bell tests, you use semiquantum tests, so you tell me, for example, that a bipartite source, lambda AB, yields better payoffs than another source, lambda prime, in all semiquantum tests of entanglement, then I can conclude, actually, it's an equivalence. It's a mathematical equivalence. So it's the same structure. That this happens if and only if the situation looks like this. So if and only if the source, which is better, lambda, post-processed with some local noise, gives you the source lambda prime. So you have a kind of realization theorem. So it tells you that source lambda, which is the one that gives you better values in semiquantum tests, is able to simulate the source lambda prime, or it is sufficient for lambda prime with transformations that are, well, if you want to be specific, are written in this way. So these are local actions synchronized by some classical variable, like a die or a clock. Like you synchronize these actions with some classical variables. So these are local operations with shared randomness. It's a very restricted set of transformations, but these are enough to characterize the order, the comparison that is induced by semiquantum games. So this is a powerful connection. I mean, the mathematical structure is tantalizing. It's nice. But as I said before, semiquantum tests can also test not only entanglement in space, but also entanglement, so to say, in time, like quantum memory. So what would be now the transformation that you have when you're comparing memories? It is this one. So you have that a quantum memory M is better than another quantum memory N, if and only if you can have this kind of correlated pre-post processing that keep only classical memory in between. So you see, if you have any quantumness being propagated from A prime to B prime, it is because there was a quantum memory in between, because the processing by itself doesn't give you anything. The processing itself only allows the communication of classical information. So this would be the actual transformation structure that you obtain for quantum memories. A correlated pre-post processing plus classical memory, which is very natural if you think about it for a moment. And okay, this is the formula, but let's skip through it. And let me come to the final slide. This is taken from a presentation of a collaborator of mine, David Schmidt from Perimeter Institute. And together with him and Denis Rosset, we have a couple of papers in which we propose that this paradigm of local operation with shared randomness, which is equivalent to using semi-quantum tests, is able to provide a kind of pleasant unification of bipartite resources that have been proposed until now in the literature. There is a huge amount of bipartite resources. I spoke only about quantum entanglement here, but that's not the only one that people considered. People consider EPR steering, Bell non-locality. Then you have no signaling boxes, quantum teleportage. You have a huge number of things, but all these things can actually be nicely summarized within the paradigm of local operations with shared randomness. I will not go into details. So this is the last slide of my talk, and let me come to the conclusions. So I think I'm on time, it's 5. I think I spoke 60 minutes on the clock. I'm happy I could maintain my promise. So the conclusion of this talk, so what I would like you to keep in mind after my discussion is that the first thing is that quantum entanglement has been the sleeping beauty of quantum foundation for 60 years. Not 10, not 20, not 30, for 60 years before someone realized that you could do something useful with it, and not just being amazed by its beauty. Like, really, like the Sleeping Beauty's story, you know, like she's a beautiful sleeping thing, and then the prince wakes her up with a kiss. So now we know what to do with quantum entanglement, and it's really useful for quantum technology. Actually, I would say it's a crucial resource for quantum technologies. And then I would like you to take home the idea that there are always trade-offs when we are testing for a property. And just taking 3 of them, quantum tomography, Bell test, and semi-quantum test, we have seen that each one has its own strong point and its weak point. And I would say that semi-quantum tests, in my opinion, are good because somehow they strike a balance between weak point and strong point. Maybe one could say, oh, they are the worst because they are neither quantum tomography nor Bell tests. But I would say that actually probably they find their usefulness in some scenarios. Yes, in my opinion, I mean, of course, I have to tell you that semi-quantum tests are those that hit the sweet spot, but you're free to disagree with me. And they can be extended, but you should, okay, maybe you can disagree with me about the usefulness, the practical usefulness of semi-quantum tests, but I would like you to agree with me about the nicety of the theory that you obtain from them, because it is from them that you have this theory of statistical comparison for quantum structures that appears to generalize the theory of statistical comparison of experiments in mathematical statistics. Yes, the order theoretic developments that are nice in themselves. And this is all, and I thank you very much for your attention. I'm open for questions.
Thank you so much. And it was a very stimulating talk.
Thank you.
And so now this talk is open for questions and answers, or if you have a comment, it's okay. Also, you can go ahead. And I would like to make just one comment that you in the beginning and also in the final slide that you said entanglement is necessary for those quantum technology, but actually BB84 didn't have any quantum entanglement necessary, but it turns out to be equivalent to the entanglement using scen using entanglement by Eckert 91. And so do you have any comment that there seems to be some technology without entanglement, but it could be proved to be entanglement, like this BB84 and E91 and something like that?
First of all, thank you very much for your comment, because there is a nice history, a nice development there, right?
Yeah.
The 1991 paper by Eckert is titled Quantum Cryptography Using Bell Tests.
Yeah.
And then there is a 1992 paper,
yeah, right,
Nassar and Mermin, where they say quantum cryptography without Bell inequality. So it was an obvious reply to them. But then people realized that actually, until I would say early 2000, okay, then people realized that actually they are essential. Like if you prove the security of one, like entanglement-based quantum cryptography, then you are also, or actually you can mathematically turn the BB84 protocol that is not using entanglement, you can mathematically turn that into an entanglement-based quantum cryptographic protocol.
Yeah.
But you're right when you say that actually BB84 does not use quantum entanglement there, but I would argue that it requires a quantum channel being being used to send the states from Alice to Bob, because if the channel is too noisy, then of course no quantum cryptography can be done. So in the sense, you can say that there is no quantum entanglement in space, perhaps in BB84, but surely there is quantum entanglement in time, in the sense that you need a truly, genuinely quantum communication channel between Alice and Bob in order for BB84 to work.
Okay, good. So, okay, any other question or comments?
Excuse me, that means related to Professor Kim's question. So I also know that there is a non-entanglement based quantum correlation, which has nothing to do with entanglement. Then in this case, I mean, people say, as far as I remember, the quantum Fisher, quantum Fisher, right? Some kind of measurement, right?
Quantum Fisher information.
Quantum Fisher information and the Bourès distance correlation, something. I mean, which also studied about non-entanglement quantum correlation and so on. Then, what is the potential the quantum technology based on this kind of non-entanglement based quantum correlation, if any?
Well, as I said, at some point, like if you don't have quantum correlations either in space or in time, you have no quantum cryptography, you have no quantum computation. Even if you think as just quantum computation, even though, well, entanglement is there because you typically use control NOT gates and so on. But still, what gives the power of quantum computation is also quantum correlations happening in time, so that the output is correlated to the input via a quantum gate, which is a unitary transformation, which is a genuinely quantum channel. So if you don't have quantum entanglement in space, maybe you can still have quantum protocols that exploit quantum entanglement in time. So when I say quantum entanglement in time, is just that I mean quantum memory. So if you don't have quantum memory, if you don't have a mean to store or to distribute your quantum system without it becoming classical, then there is no quantum technology there for you. On this we agree, right? I mean, if you have no way to keep your system quantum and it just decoheres, there is this word decoherence. So if everything that you have in your laboratory is just decohering very quickly, there is nothing you can do with those. So either you need entanglement that allows you to beat decoherence by means of teleportation. But again, in teleportation, you need memory, right? Because Bob needs to keep its quantum system alive until Alice's outcome are communicated. So Bob will need also quantum memory there. If everything collapses on a classical state, then there is nothing we can do interesting with that.
Okay.
I don't know whether that answers your question, but.
Hello?
Yes.
You can ask a question. Oh, okay, that was your voice.
Sorry, you
Okay.
didn't hear my answer?
Oh no, I heard it. Yeah, okay, that's okay. Good. Yeah. And so this is mostly about this the non-locality, and also we can think of a contextuality without non-locality. So could you tell us a little bit about this implication of this your argument on this entanglement in the context of contextuality?
Right. Well, in that case, well, of course, it depends how we define rigorously contextuality, right? For example, one could work with compatibility of measurements. But again, you always need some kind of quantum memory. Even though, what I would like to say is that even though quantum entanglement is not there apparent to be seen, like even if you don't have two space-like separated parties that share quantum entanglement, it is always kind of lurking in between, it's lurking behind the scenes in the form of quantum memory. So it's always about being able to keep quantum correlations either in space or in time in order to achieve a separation from classical statistics. If we don't have that, then everything that we can do can be just described by classical probability distributions. And contextuality would be the same, but also compatibility of quantum measurements. We had a contribution with Eric Chitamber and a PhD student of mine, Joe Wemby, where we show that there is a strong connection between compatibility or incompatibility of measurements and quantum memory. You can always turn one into the other and vice versa in a resource theoretic setting. Without going too much into the details, but everywhere you look, you will always find quantum correlations going on in quantum technology.
And also you mentioned this rotation of a space-like separation into the temporal separation. And so is that the temporal entanglement you are talking about, or something else?
When I speak about, so I know that there are issues that, well, when I do the rotation there, it's really like something intuitive. I'm just taking my drawings and then rotating drawings. I'm not implying anything like Vic rotation or things where you go from a real time to an imaginary time, nothing of that. Mm-hmm. It is really just a kind of intuitive picture. I'm just saying, let's turn a space-like setup into a time-like setup. That's the only thing I mean. But I know what you mean, and I know that there have been discussion about what it means to have temporal entanglement, whether when I speak about entanglement in time in this talk, I'm just using the very orthodox understanding of it as a quantum channel. So like a channel that is able to transmit something more than just the cohered states, that is able to transmit some quantum coherence, so to say. So when I speak about temporal entanglement, it's just a quantum channel. That's nothing so there.
Okay. Okay. I do not see other questions. So the
excuse me. Let me ask you a question, Francesco.
Yeah. Okay. Go ahead. Yeah.
Yeah. Again, I appreciate your interest in talk. I learned a lot. But let me have 2 more questions, Francesco, if you allow me to do that. I mean, first of all,
please go ahead.
Also about, I mean, let me ask it this way. I mean, I wish everybody else in this, on this the online talk. I want also participate. Other people also participate this discussion. So let me ask step by slowly. Okay. So first of all, you mentioned us about in the beginning also mentioned about also local hidden variable theory and so on. Okay, which was violated and originally introduced by Einstein and so on. Then paradox and so on. It was kicked out from quantum point of view. But the question is, as far as I know, there is also a different version of the hidden variable, so-called non-local hidden variable theory. I mean, which is related to Bohm's mechanics. And did you also study about that as I mean in terms of a non-local hidden variable theory?
Well, I know about Bohmian theory, and actually you can imagine that. So in the EPR paper, basically what they tell you is that 3 sentences they cannot be true at the same time. One sentence is that quantum theory is correct. Another sentence is that quantum theory is complete. And another sentence is that this notion of local realism that they give, so that these things, they cannot be compatible. So EPR would suggest to reject the notion of quantum theory as being complete. So they would say there must exist some other theory, like a deeper theory, as you said, with some hidden theory, so this hidden variable that is able to explain deterministically the outcome of a quantum measurement. But another possibility is just to give up only the local part of it, so the local realism. And indeed, Bohm in the 50s came up with a model of a local, with some hidden deeper theory, so to say, but that, to use Bell's word, is grossly non-local, like that you have this pilot wave that, you know, is instantaneously everywhere in the entire universe, right?
Yeah, even more non-local than also, yeah. You know,
so yes, I never worked in that. Like, I strongly believe that locality is an important requirement of physical theories. Like everything that is highly non-local, I would look at it as a pathology, like things that happen in quantum field theory. When you have non-local effects in quantum field theory, that are signs that something is wrong with the actual formulation of quantum field theory. And there are plenty of non-local effects in quantum field theory. And in the same way, I would think of Bohmian mechanics as a very important contribution to the logical foundations of quantum theory, because it is essentially the only viable alternative to quantum theory. But I would look at it as I said, as a mathematical, as a, so to say, a mathematical entity, a logical entity, but on which we should not put any strong interpretation, however. So you know, in a sense, how to say, one can be Bohmian, right? And as far as I know, I don't know, maybe I'm adventuring myself in things that I don't know very well, but as far as I know, there wouldn't be any experiment that would be able to rule out whether nature is actually Bohmian or not. So that is just a choice of religion. Right? Like, one can choose to be Bohmian, one can choose to be Copenhagen. And in a sense, I find locality more compelling than realism. But I understand it's a big jump. For other people, it's better to give up locality and keep realism.
Yeah, sometimes they call it jokingly Bohemian.
The second question is,
second question, go ahead.
Yes.
The second question is, you also mentioned during the discussion with Professor Kim, you mentioned about the early work of David Mermin, and in doing so, he, as far as I remember, he also, you know, mentioned about quantum non-locality without using, you know, Bell's inequality and so on. Mm-hmm. Then at the time, to my understanding, this the discussion non-based on Bell's inequality was performed basically for, you know, GHG state. I mean, 3 two-level systems, for example. Then what about your case? You mentioned us about the semi-quantum test.
Yes.
What about, to my understanding in your talk, beautiful talk, that you mainly primarily focus on two-level systems, two-partite system. What about three subsystems, which might be, you know, applicable for GHG state, for example?
Yes, it's a very nice question, your question, and indeed we consider that. It's a natural direction to look into. And indeed, you can use semi-quantum test to probe correlations also among many parties. Already in the original paper back in 2012, I wrote a short note at the end about that case. But then it's been developed more by someone else, I think. But now I cannot really remember who was that. But Yes, I mean, semi-quantum tests can be used also in a multipartite set scenario.
So that this is in process, basically, in process. You are looking at that.
No. I've been, I mean, there is something already in the original paper in 2012, where I show one very natural, I would say, obvious way to generalize this approach to multipartite scenarios. But then this was brought to a deeper level by someone else, which I don't remember exactly whom now. Off the top of my head, I cannot really remember who did it, but someone who gave a much more thorough analysis of semi-quantum tests in a multipartite scenario.
I see. Okay, thank you. It's good.
You're welcome.
So anyone in the audience can help Francesco's memory of those papers? Okay, now it's about time to finish. And so let's thank Professor Francesco Buscemi. And we are expecting another interesting talk next week by Professor Valeria Scarani. And also don't forget to register for the AQIS 2020 Sydney online. And that's registration is free. And you are going to enjoy very nice talks. And also you can see a lot of contributed talks there. Thank you very much, everybody, and also Professor Buscemi.
Thanks to you for your attention, for your time.
Okay, bye.